Okay, so the last thing we want to look at in regards to integration is, okay, what about doing more than just a double integral, right? Like we saw with partial derivatives, we could just keep taking the partial derivative. That's kind of the same idea with integrals, is we can just keep taking the integral, right? We could do a double integral, we could take a triple integral, etc. But you can imagine for a second that as you add on more variables, it's going to get more complicated. In the easier cases, like where you're just doing a quote unquote rectangular region, which wouldn't be a rectangle anymore, because now we're going up to three dimensional domains. We we're two things. We're going to have a hard time visualizing what the region we're integrating over is. Okay, so when we're looking at double integrals, we can visualize the region we're integrating over, and we can kind of imagine the function, at least with the help of a 3D graphing tool. And we can kind of put those together and get a good idea of what's happening. With triple integrals, now our domain that we're integrating over is three-dimensional. So just relying on the domain, it's going to be hard to draw a picture of it. And then you need like a 3D graphing tool to really get a good picture of that. But then the function itself is four-dimensional, so we don't even really have any hope of visualizing what's happening there. Now, if you jump up to, quadruple integrals, I guess you could say. I've never heard that term before, but I'm sure it's used. But when you have four integrals of a four-variable function, now the domain is four-dimensional, so you can't even really visualize that. And we've been pretty dependent on visualizing the domain, right? We always start by drawing a picture of it. And we don't have to do that, but it definitely makes it a lot easier, and it's going to be hard if we can't do that. So that's really the main difficulty, I think, once we start jumping up in how many integrals we're doing. The next part, which makes it more difficult, maybe even more difficult, is that if we do need to change bounds, we all of a sudden have more options for how we change those bounds, right? Because we have three integrals now. So we could change them over to, if we have x, y, and z, for example, we could change them over to z functions or to y functions. And once you have four, now you have a lot of different choices for changing those bounds around. So, and as we saw, it's hard to know ahead of time which function you're going to want to integrate with respect to first. So now if you're adding more integrals into the mix, you have more choices and more areas to run into trouble and, not knowing how to turn it around. So for that reason, a lot of the triple integral examples are going to be pretty basic functions where you don't really need to worry about that. But, if there was a real world scenario where it came up and you needed to actually do that, it can be pretty complicated. So we'll look at what the equivalent of a rectangular example would be. I guess you could say cubic, but it's not going to be a cube every time, right? I don't even know what a rectangular version of a cube is called off the top of my head. Like a rectangular prism, I guess. But anyway, that's kind of how the region will be defined. So we'll just learn by example here because there's not really any new theorems to look at. So let's go from 0 to 1, 2 to 4, -1 to 5 of x plus y z squared dx dy dz. Okay. So these are the x coordinates, these are the y coordinates, these are the z coordinates. Okay. So you could probably flip these around as you want to because all the bounds are just constant. It shouldn't really make too much of a difference here. So we'll just go ahead and take it as is though. Okay, so here when we integrate with respect to x, we're going to get x squared over 2 plus yz squared x. And then we're going from x equals -1 to x equals 5 dy dz. Okay. So we'll plug our bounds in. So x equals 5, we're going to get 25 halves plus 5yz squared, and then we'll have minus 1/2 and minus a negative, so plus yz squared dy dz. Okay, you could go ahead and simplify that a little bit before carrying on with the remaining integration. 25 halves minus a half is going to be 12. 5yz squared plus yz squared will be 6yz squared. Okay, then dy dz. So now we integrate with respect to y. Okay, so this is going to be 12y plus 3y squared z squared. And then we'll plug in our y bounds. Okay, so y equals 2 to y equals 4 dz. So now we have 0 to 1, so that's going to be 48 plus 48 z squared. I think I did that right, yeah. Minus 24, and then minus 12 z squared, dz. So we'll go ahead and simplify that again. So we have 24 plus 36 z squared dz. So then finally we just integrate with respect to z. So it's going to be 12 z cubed, and then we'll plug in z equals 0, z equals 1. Okay, so we'll get 24 plus 12, so we'll get 36. Okay. So basically the exact same process, just have one more integral to do. So it's like if we just like took our answer from the last step of one of the last ones and then just integrate it again with respect to z or something like that, right? So let's look at one with a more general region now. Okay. So this one we want to evaluate f of x, y, z equals 5x minus 3y over the solid tetrahedron, which is like a just like a three-dimensional four-sided surface of some sort, I'm assuming, bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay, so we did a problem that was pretty similar to this before, but the difference here is that now we have a 3-variable function rather than a 2-variable function. Even though that third variable isn't in there, it still is a 3-variable function. So first we really need to define the region, because it's not going to be as simple as it appears, right? I think the appearance here, the book calls this region E. They're using E now for the 3-dimensional one instead of D, but it doesn't really matter. I think it's clear using this bound, you can set it so that you can write this in terms of any of the variables. Usually most people would just pick z because it's the last one there. And you'd say z is equal to 1 minus x minus y. So z is going to be bounded by 0 and the function 1 minus x minus y. So now let's think of another variable, say like y. So the first one that we set up kind of defines our limits on the xyz plane, so that 3-dimensional coordinate system. But then we need to define our limits on the xy plane, or whatever your two remaining variables are. So if we think about what this would look like on the xy plane. The xy plane would be where z is 0. Okay, so if z is 0, then you're left with, given that condition, you're left with x plus y is equal to 1. Right, so on the xy plane, z is 0, which implies x plus y is equal to 1, which implies that y is equal to 1 minus x. So y is going to be bounded by 0 and 1 minus x. Okay. So first one, you're defining where you are on the three-dimensional system. Then you want to define kind of where you are on the two-dimensional system. And then finally, the last one is just an interval, the one-dimensional system. So there could be different answers depending on which variable you're choosing to do this with. But they'll all be equivalent. So this is going to be 0 is less than or equal to y is less than or equal to 1 minus x. And then finally, x, the last step, is kind of like the fill it in step, where you're just going through all the values now. So this goes from, x is going to go from 0 and then just to 1, right? 1 is the absolute largest value of x, which would happen if y and z were both 0. Okay. So this, the second step right here, I think, is the one that is maybe the unexpected one, right? Like we kind of expect this is how this is going to go based on what we did with double integration. You know, this one's going to happen, but we still need to define kind of our boundary in the two-dimensional space. I do recommend looking at this problem in the OpenStax textbook. Again, that's OpenStax Calculus 3. This is in the section 5.4, Triple Integrals. Look at figure 5.45, which kind of gives a picture of this and shows it a little bit better, which is, you know, hard to do three-dimensionally because the picture is three-dimensional. So now if we just go ahead and, you know, look at the integral, we're going to look like this. 5x minus 3y dz dy dx. Okay. So we go ahead and do the first two, or do the first one. So 5x squared over 2 minus 3y squared over 2. Sorry, I don't know why I just did that. We got to integrate with respect to z, not with two different variables there. 5xz minus 3yz from z equals 0 to z equals 1 minus x dy dx. Okay. So, and I just wrote the wrong bound again. 1 minus x minus y. Right, so this is going to be 5x, 1 minus x minus y, minus 3y, 1 minus x minus y, dy dx. So you probably just want to multiply it out right away. And you know, just like before, like a lot of the I don't like saying the bulk of the problem is in the setup because it's really usually the shortest part, but the most like intellectually challenging part, conceptually challenging part is in the setup. The rest of it's just kind of grinding out the integral using the techniques we've been using since Maths 2, right? So not a lot of new stuff going on in these parts. I guess plugging in variable bounds is a little bit different. So here we're going to integrate with respect to y now. So we have 5xy minus 5x squared y minus 5 halves xy squared minus 3 halves y squared plus 3 halves xy squared plus y cubed. And we're going from 0 to 1 minus x. Okay, so now we'll just go ahead and plug those in. It's going to get pretty long at this point. So maybe I won't spend time going through the mechanics of this, because I think that at this point, again, it's just kind of long. There's probably ways to make it shorter. I guess not really. You can't really combine too much here, but I'll just write what the answer ends up being here, which is 1/12. If you want to just go ahead and grind that one out. I do want to just go through at least the setup of another one, because again, I think that's the key part in these. I really want to focus on, for another problem, is how do we go ahead and change these bounds? Because what you can imagine here is that you can't just change just one of them like we could before to the other one. Now you have multiple different bounds, and it's going to kind of have this cascading effect where when you change one of them, you're going to have to change other ones around as well. So, and there's going to be multiple ways that we can do it as well. So let's go ahead and look at this one. So this one says we have the integral from 0 to 1, 0 to x squared, 0 to y squared of fxyz dz, dy, dx. Okay, so this tells us that z is these coordinates, right? Y gets these coordinates, etc. Okay, so we have multiple bounds to consider here that are functions instead of constants. So the region that we're working on is xyz, such that 0 is less than or equal to x, less than or equal to 1. Y is between 0 and x squared, and z is between 0 and y squared. So now what if we want to change these around? Okay, what if we want to do x first, or something like that? How do we go ahead and do that? So the best way to think about this is by dividing it into two-dimensional spaces, because again, we can't really picture the three-dimensional spaces too well, but we can picture two-dimensional spaces pretty well, right? So we want to break it down into the two-dimensional space. So what are we looking like on the xy plane? What are we looking like on the yz plane? And what are we looking like on the xz plane? Okay. So xy plane is where z is 0. YZ plane is where x is 0. XZ plane is where y is 0. Okay. So this is going to be xy, such that x is between 0 and 1, and y is between 0 and x squared. Okay. Now this one we can pretty easily see how we would change it around, because we've already done this, right? If y is between 0 and x squared, we could change this around to, let's see if I can squeeze it in. X being between the square root of y and then 1, which is what it was bounded by before, right? So in other words, you could kind of draw this one out as we normally would. And we'd say, okay, we have y is between 0 and x squared, x is between 0 and 1. So we're on this region right here. And we can see that we can translate that to x being between the square root of y and 1. Okay, we don't need to worry about the negative square root of y part, because y is always positive, so that didn't really come up anyway. And then the y part, which we can see here, the lowest value of y is 0, and the highest value of y is 1. Okay. So that gives us a way to change around the coordinates. The YZ plane is the YZ points where Y is between 0 and 1, Z is between 0 and Y squared, XZ plane is the XZ points. So here, again, X is between 0 and 1. And now this is a little interesting. We got to think about, okay, what is Z defined by? Because Z was only defined by Y squared before. So we could kind of get an upper bound on Z, like namely, if we wanted to graph it, we can see Z is less than Y squared, Y is less than X squared. So that would tell us that Z is less than or equal to X to the fourth, right? Which would be X squared squared. But we don't really know how much like room there is between these two, so we don't know if that's like if Z goes all the way up to X to the fourth or not. So we'd probably just write it with the Y squared still, even though there aren't really any Y points on this part yet, but that's really the only exact bound that we can get there. Or we would just write it like X to the fourth, or whatever. Okay. If we really didn't want to have a Y in there. So when we go to do the integral, then the only one that we actually changed effectively was this one. We changed the X and the Y's around. So the Z, we can still just use this bound that we have right here. But there's going to be a lot of different ways that we can rearrange this integral, all with, changing the different ones. Like if we change Z, if we change this one to be like Y is greater than root Z or something like that, right? Then we can change it that way. So with the double integrals, there was effectively 2 ways we can write it. With the triple integrals, there's going to be effectively 6 ways we can write them, right? And some of them might end up being the same. But that means that we can write this integral ultimately then as 0 to 1, 0 to y squared, root y to 1 of f of x, y, z, dx, dz, dy. Okay. But again, there will be, so we've seen 2 ways to write this integral now. So there should be like 4 more ways. And again, some of them might be the same. But yeah. But it can be really tricky to think about this. So we really want to kind of like decompose the regions and see how everything changes. Here effectively, we basically, like to do this one, we just effectively ignored the Z1 and just changed it like how we would have in the double integration case. So you can kind of just think of it that way. With these is just changing like 2 at a time and leaving 1 the same, right? So maybe we change here we changed around these 2 and left this one the same. Maybe we change around these 2 and leave this one the same. So just things like that. But if you decompose them into the different planes like this, it can help you a little bit to see exactly which ways you can switch them around.